So ABX test, we are very much familiar with this term, ABX test. It's one of the most popular types of listening test conducted in audio industry. You can compare PCM CD quality audio versus MP3 low bitrate audio codec. And X is basically either PCM or MP3 randomized, and you need to select well, you need to identify which one is X, basically, between A and B. Well, it could be used for high resolution audio comparison, for example, between 48 kilohertz versus 192 kilohertz high resolution audio. It could also be used for hearing threshold type of test. So A could be a silence and B could be a tone at a really low level, and you want to see whether the observer can discriminate between silence and tone. I mean, it's about detectability, and this ABX methodology can be used for many different things, and it's been used a lot in food science and vision research, speech, linguistics, psycholinguistics area. A lot of people use this methodology, but today's talk is about how should we conduct this ABX test? How should we design it correctly? And also, how should we analyze the responses from the subject, and how should we report the result? And also, is ABX test the right thing to do, or can we use some other methods instead of ABX? So I'll give you a bit of a history lesson. The test method was first proposed by Munson and Gardner in 1950s. I just quote from their abstract. Basically, this test was designed so that the observer is presented with a time sequence of 3 signals for each judgment. So I highlighted this part, presented with a time sequence. Actually, later I'll introduce a different kind of way to do ABX test, which has become more conventional in modern times. But this is actually one of the main discussion topics for today, whether we should use this time sequence method or random access to A, B, and X, and the listener can freely switch between all of these stimuli without any time limit. This ABX methodology was, as I said, it was first developed in 1950s, but sometimes I found that David Clark was cited wrongly as the inventor of ABX test method, but it's not correct, because he set up this company called ABX test company, and they invented this first commercial hardware product for doing ABX test called AB comparator. This allows the user to control everything, basically. So it uses this random access method. You can select between A, B, and X yourself. You can switch back and forth among these 3 buttons, and then you can do your comparison in any way you like. So the transition direction can be reversed, A to X or X to A. And the listener may temporarily wear out one detection mechanism, but can listen in a different way, hearing another manifestation of the difference. So a similar product was developed by QSC, ABX comparator, in late 90s. But there are a lot of free software tools that audiophile people use for comparing different types of audio materials. There are a lot of these freely available tools. They all allow the user to switch between A and B and X, and this random access is allowed, and also even region selection, so you can actually listen to specific time region unlimitedly. So you can listen to it over and over again until you are satisfied with your decision. And there are some most freely available research tools for doing ABX test. And most of the tools also allow unlimited user-controlled switching. So there is no time limit and there is no specific time sequence. You can just press the buttons and compare all of these three sounds and determine which one is X. But there are some tools that strictly follow the time sequence method. So once you press play, A will be presented first, and after a short time gap, which is typically about 300 milliseconds or less, and then you hear stimulus B, and then finally stimulus X, which is either A or B, randomized in each trial. So really the question here is, what kind of methodology should we use? I mean, should we allow people to have random switching and should not limit the time duration they can hear the samples for? Or should we follow the strict time sequence rule, which was originally proposed by Munson in the 1950s? We are so used to switching between different stimuli in audio evaluation tests, like Mushra, for example. We can freely click on different stimuli and compare the audio quality and rate the relative differences between all of the stimuli. And they are mainly from ITU-based methods. But in psychophysical test, psychoacoustic test, so strictly speaking, when we aim to measure a person's discrimination ability, or if we want to measure a perceptual threshold, like just noticeable difference, a strictly controlled procedure is very important for obtaining reliable and analyzable data. So this is just a summary of some existing methods, but there are different procedures. Basically, there's non-adaptive procedure and adaptive procedure. And also, there is a model for discrimination task, high threshold theory versus signal detection theory. These are the classic methods, basically method of constant, method of limit, method of adjustment. But there are methods you can use for measuring sensitivity and bias, and also some efficient methods like staircase method, which is a dynamic method. The level of the next trial is determined based on the your decision of the current trial. So I want to talk a little bit about problems with this unlimited random switching method. The first issue is potential bias. So the more you compare and listen to the samples, then you want to find the right answer, and you might even be very much obsessed into the task, and you can maybe just listen to the samples millions of times and you can't still make a decision, because the more you listen to it, the more you may get confused, especially for trials with very subtle difference. So this bias factor should be really considered in the ABX test design, I believe. And also another problem is this random access method might change the decision strategy randomly between this independent observation model and differencing model. So you can find more details about these different decision strategies from these references below. But basically what independent observation means is that you have a comparison between A and B first, and then you listen to X, and then determine whether X is A or B. So it's very much based on this time sequence. So you have A presented first, and then B, and then finally you make a decision about X. I mean, in audio testing, we inevitably have this time sequence approach, but in vision research or anything you can visually compare on the screen, you have A, B, and X all together. And then either way is possible. You can firstly compare A and B, and then look at X and then see whether X is A or B. But you can also use the other method called differencing method. So you strictly compare the difference between A and X, and then also difference between B and X separately, and then see which one has the smallest difference. And that way you can make a decision whether X is or A or B. So the problem here is with random access and unlimited switching, your decision may be biased while you're doing these mixed approaches, because if there's no rule, you can go for independent observation a couple of times, and then you can try differencing methods a couple of times, and then go back to independent, and so on. And this also does not allow us to calculate sensitivity D prime value correctly, because D prime value for ABX test, it depends on whether your decision strategy was independent observation or differencing observation. So later I'll show you an example table, and you can see there are two options you can choose from depending on the decision strategy. And also some researchers found that the ABX test was prone to high cognitive load, and also from Joshua Rice's great review paper on high-resolution audio, he's done very extensive meta-analysis on previous high-resolution audio research papers, and he concluded that previous research may be prone to these false negative type 2 errors because of the potential bias. And another issue with this method is test duration and listener fatigue, because listeners can listen to the sound many times until they are satisfied, and sometimes they never get convinced about their decision, and they keep going on and on. So the test may not be finished actually, and it could actually take a long time until you finish all the repeated trials. And this can eventually lead to listener fatigue, and you may be biased because of that. And also this makes it difficult to include many trials for each condition, because it may take 10 minutes for completing one trial, and you cannot repeat it 100 times for each listener. And also there's some issue with the analysis and reporting methods. A lot of studies using ABX method recruit many subjects, but each condition is tested only once or just a few times per each subject, and then obtain the percent correct value and cutoff level from everyone's responses pulled together. So if you have only 25 people, let's say, and they test each condition just once, and then you have 25 responses, but that's not the correct way of doing this kind of psychophysical test, because you're essentially testing individual sensitivity and bias, and you want to know whether each specific observer, each subject can pass or fail the test. So the percent correct must be initially calculated for each individual subject, multiple responses, and then you can see the average percent correct across the whole subject, and also talk about sensitivity and bias. So even if you have only 5 subjects, if you repeat it 25 times for each condition per each subject, and then you can gather results like this. I'll talk about this a little bit more later, but you can discuss each individual person's ability to discriminate differences between different conditions. But if you have 25 subjects testing each condition just once, and then you may have a false conclusion, because all these different subjects might have experienced different biases during the test, and they all have different level of experience and sensitivities. So just using 25 responses and conclude that everyone could hear the same thing, everyone could lead to the same conclusion, it's not scientifically valid. So how do we conduct an ABX test in a psychophysical way? So if we strictly follow this psychophysical methodology, an ABX test is essentially what we call 3-interval 2 alternative forced choice method. So if I quote Munson and Gardner's again, an observer is presented with a time sequence of 3 signals for each judgment. So you have A first, after a short amount of time, and you hear B, and then finally X. And the time gap should be fixed. And I found about 250 milliseconds is appropriate. It's okay, because we need to think about a short-term memory issue. If the gap is too long, you may forget what you heard in previous stimulus. And a single presentation of A, B, and X in each trial, and no switchover should be allowed. And instead, you need to repeat the same condition many, many times. The more the better, of course, but there are practical constraints. So at least 20 to 25 repetitions recommended. The test duration is then consistent for all subjects because you fix the time gap and you have the set amount of time allowed for each trial to complete. So you can actually predict the test duration before you start the experiment. And from my experience, this makes a huge difference in terms of listener fatigue. Because if you just let the subject to compare A, B, and X, however long they like, it can take hours, to be honest. But if you set this duration, the time gap, and repeat it a certain amount of times, you already know how much time you need for each test. And another point is that the number of trials with X and X equals A and X equals B should be identical. This is for signal detection theory-based sensitivity and bias analysis later on, which I'll talk about later. And when you analyze ABX test responses, typically pass or fail is determined based on the whether the percentage of correct responses, percent correct, is above a certain cutoff level. And for this, usually we use binomial test to determine the cutoff level, above which the probability of passing the test by chance is lower than 5%. Typically, we use P below 0.05 for 95% confidence level. And for this, this cutoff percent correct becomes smaller as the number of trials is larger. So you have more and more trials, then the cutoff level will become closer to 50%. So for example, if you have only 10 trials, 10 repetitions for each condition, then the cutoff percent correct should be 76.4%. So you need to have higher percent correct than this in order to pass the test. But with a larger amount of trials, if you have 20 trials, then this value becomes 69%. If you have 100 trials, then it becomes 58.7%. So for example, this is a test result from one of my students, ABX test for CD quality versus MP3 at different bit rates, low bit rate audio codecs. Sorry, actually it's not MP3, it's AEAC, low bit rate audio codec, and 26 trials per subject, and 67% cutoff level. So you can see quite a difference between these 5 subject results. So for example, subject 1 passed the test for 32 kilobps. Obviously, there are a lot of artifacts one can hear, but 48 kilohertz and 64 kilohertz, this person couldn't really hear any difference. I mean, well, heard some differences, but the cutoff level is at 67%, and the result is below that threshold. By the way, this is a mono condition, so 48, 64, they correspond to 96 and 128 in stereo. But this particular subject, 5, had the results, the percent correct were all above the threshold cutoff point. So this person passed all of these conditions. But it varies across different subjects. So we need to firstly analyze the results for each person, and then we talk about general trend and maybe average percent correct values. But this threshold should lie at this particular value for each of the person, not for the whole responses from everyone. So this percent correct based decision is not enough because of some limitation of ABX test. Because if we think about potential bias that might occur during the test. For example, short-term memory issues has been pointed out by several researchers. So for example, by the time X is presented, the auditory traces of A and B may have faded from the listener's memory, especially when you go through this time sequence. And also, some researchers found that ABX task is subject to strong bias towards B, because you hear A first and then B later, and B is close to X in temporally. So people may be biased towards selecting B instead of A. So this was found in this paper. So we need to consider potential bias as well as percent correct and sensitivity. Of course, what we're mainly interested in is the percent correct and sensitivity, because we want to see, how much there is audible difference one can hear. But we need to take the potential bias into account when we interpret the results. So I'll talk a little bit about signal detection theory now. For those who are not familiar with this theory, it's just a bit of introduction. So basically, signal detection theory is interested in sensitivity and bias rather than threshold. So usual threshold model basically relies on the psychometric function. So you get percent correct values for each and every condition, and then you derive a psychometric function. And then you find this point where this correct answer rate is 50% in case of yes/no task. And that is the most common way of deriving threshold. But signal detection theory basically assumes that there's no threshold. There exists no threshold because there's always a certain level of bias involved in our decision-making process. So we need to look into the bias criterion. This is a measure of bias, decision criterion C, and the D prime is the measure of sensitivity. The source of bias could be many things, like your mood on the particular day, your state of mind, your health conditions, or external noise. I'm hearing my children's background noise because my daughter just arrived from nursery, and she's they're making noise outside, and it's kind of affecting how I'm talking. So there can be a lot of different biases involved in our decision-making process. So how do we calculate then the D prime and the criterion C? So all we need to know is the hit and false alarm rates and the Z-score for the hit and false alarm rates. So let's take an example here. If we go with this traditional yes/no task, a simple question is asked, did you hear the signal? And you're presented with either signal plus noise or just noise. And then you need to make a decision whether you heard the signal or just noise. And when the stimulus is signal and noise, and you say yes, then it's hit. But when the stimulus was noise, but you said yes, and then it's basically false alarm. But if the stimulus was noise and then you say no, then it's correct rejection. And the last condition is obviously miss. But if we apply this to ABX task, then we only have hit and false alarm because there are two conditions, either X equals A or X equals B. So for the trial with X equals A and you report A, then it's hit. For trials with X equals B and you still say I heard A, then it's false alarm. And the opposite case for this X equals B, and you say B, then it's hit, and the other case is false alarm. So let's take an example here. 100 trials of ABX task with 50 trials having X equals A, with the other 50 trials that include X, which is B. So these numbers should be the same ideally. You need to have equal number for X equals A and X equals B. Then we can calculate the hit and false alarm rates. So let's take an example. Subject A did 100 trials, and this person got 40 correct answers. So basically, when X was A and the answer was A, 40 times out of 50 conditions for this particular scenario. So you have, out of 50, you had 40 correct answers. But this person also said, when X was actually B, this person said, I heard A. So there are 10 false alarm responses and 40 correct responses, which are hits. So you can see that in either case, when X was A or B, the correct answer, the number of correct answers was equal. So 40 hits for A and 40 hits for B. And in total, the percent correct is 0.8, 80% of correct answers. And let's have a look at subject B. In this case, we have some different results. So still the percent correct is 80%, 47 for A and 33 for B. In total, we have 80%, same as subject A, but now the numbers are different for these two cases. So let's have a look at how this affects sensitivity and bias. So a little bit of numbers that we will talk about. So firstly, for 100 trials, we have cutoff level of 58.7%. So the correct answer needs to be higher than that. So percent correct is 0.8, which is bigger than the correct the cutoff level. Then basically this means that this person passed the test. But if you look at hit rates and false alarm rates, we can easily calculate them from these numbers, HA, HB, FA, and FB. And then we need to find the Z scores for these hit rates and false alarm rates, which are these. And then the criterion can be calculated easily by using this equation. So in this particular case, we use the HA and FA, and then you can see that the criterion value is 0. So 0 value of C basically means there was no bias, which effectively means, you know, the number of correct answers for A and that for B is equal. This is an ideal scenario, because in practice, you know, when there is no bias, these numbers must be the same because they are the same condition, but reversed in order. Basically, A and B is still the same. So these numbers need to be the same. And we can also calculate sensitivity value D prime using this equation. Firstly, you calculate the difference between hit rate for A and false alarm rate for A. The Z-score difference is this. And then we eventually get this D prime value from a table provided in Macmillan and Creelman's book. This is kind of a Bible for you know, this kind of discrimination and signal detection theories. So if you're interested, you can get this book and get more details. But you see that for ABX test, there are two options: independent observation and differencing model. So we need to choose the right one depending on how you design the test. And in our particular case, the D prime becomes 2.07, which is high sensitivity, basically. If you have any D prime value bigger than 2, that means it's fairly audible. It's a big difference. You can detect easily. And there's no bias, which is an ideal case. But for, so if we look at the probability density function for this particular result, the normal distributions for HA and HB, and the criterion lies right in between the two. There's a certain level of false alarm and false alarm for A and B, but it's not a lot. We have majority of the responses given to HA and HB, and criterion lies in between. That means there is no bias. But this subject B also has the percent correct of 0.8, still passes the test, but there is some bias present here. because the number of correct answers for A and B are different now. And going through the same process, we can get this criterion value of minus 0.571. And the sensitivity is 2.31. So it's still high sensitivity, but there was a bias. So that basically means that the criterion has been shifted to the left, which leads to a biased decision towards A. So there's more A. So this person was inclined to say A more than B, but then at the same time, it increased the chance for false alarms for A. So in this way, we can identify which person actually was biased during the test and how. If we compare these two sets of results back to back, now, even though the percent correct is the same between A and B subjects, the bias factor is different, of course, but the D prime, the sensitivity value is also different. So for subject A, it was 2.07, but for subject B, it was slightly higher, 2.31, even though the percent correct is the same. So what does this suggest in practice? Basically, in signal detection theory, having the same percent correct despite the bias means that the sensitivity for this condition, it was higher. So you have this bias, but even so, you still have the percent correct of 0.8. That means the sensitivity was greater than the other condition. Probably skip that bit. So lastly, I'll just go for 4 more minutes. So is ABX the right method to use? So now you see that ABX test is not perfect. And there are some criticisms about ABX testing in audiophile community and research communities, but I personally believe that a lot of false negative results or even false positive results were obtained because of incorrectly designed test methodology, and a lot of bias has affected the result. So ABX test is more suitable for understanding if an overall difference rather than a difference in a specific attribute is audible between the two samples. So for example, high resolution audio, we still don't know what actual differences we can hear. So ABX test might be a right one, but if you already know what specific attributes you can hear between two samples, then it's always better to actually ask specifically about the attribute, not just overall difference or ABX test. Because the potential limitations are the confusion and listening fatigue during the self-switching process, and also the short-term memory issue presented in the time sequenced method, because there are 3 intervals, and you may forget about A while you're listening to X. Yeah, so I already mentioned that, in order to reduce bias and increase sensitivity in our decision making, it's better to focus more on the specific attribute. For example, if you already know that 70 dB and 70.5 dB, if you compare these two signals, then theoretically the 70.5 dB should be louder than 70 dB, but this is an objective value, but can we actually hear it? Then we can ask this question, specifically, which one is louder, instead of doing ABX? This 2 sample comparison scenario is what we call 2 interval, 2 alternative voice choice test method. Or sometimes it's called 2 IFC, 2 interval voice choice, or temporal 2 AFC, because you can also have spatial 2 AFC when you have 2 pictures on the screen and you choose which one is brighter or darker. Or in audio test, it's always interval based time sequence. So the advantage is that the listener has to select a louder sample. This is a more clearer task. Basically, the attention is drawn to the specific attribute, which is loudness. And there's less chance of guesswork, because you need to specifically choose a particular stimulus. And this also has less of the short-term memory issue, because there are only two stimuli. You can also use this for doing MP3 testing, because we already know MP3 is supposed to sound rougher. We know all the possible artifacts, so we can be more specific about the question. And you can also use this SDT paradigm for analyzing sensitivity and false alarms for 2AFC tasks. But when we compare 48 kilohertz standard quality and 192 kilohertz high resolution audio, can we ask this question, like, which one sounds more what? I mean, we don't really clearly understand what kind of differences we can hear between the different formats. And this is still, there's a lot of debate about whether we can actually hear the difference or not. And we are not at the stage of talking about what actual differences are they. So in this case, it's actually better to have an ABX test, I believe, but design it in a way that there is potentially less bias and less listening fatigue and more straightforward actual analysis. So Josh already pointed out in his paper this reference here. There are potential biases in previous research, and they might have led to false negative results. So when there is actually a difference they can hear, they said, the results suggest that there is no difference. But I believe this is partly because of the test design. And yes, no task is not ideal. I'm not going to go into that in more details because there is always prone to heavy bias, and listeners can always say just yes or no, and more guesswork is involved. So when we design an ABX test for something like high resolution audio testing, we need to carefully select the stimulus type and duration. It shouldn't be too long because of the short-term memory issue. And listening training is necessary if the listeners are not familiar with the stimuli. And technical factors, also discussed in Josh Rice's paper. A careful experimental procedure, time sequence single presentation with the repeated trials is what I recommend. And personally, it really saves time and avoids listening fatigue, and potentially can lead to higher percent correct and higher sensitivity as well. So I'm in the process of designing a formal experiment comparing all these different possible methods and see which method actually leads to a better result. So hopefully I'll have some useful results to present in the future. So just a plugin, there's a tool that you can download for free for conducting all these psychophysical methods, like I just described, ABX test, 2AFC, as well as Mushra and other types of methods. You can visit this website and download the tool. You can also do binauralization of multi-channel signals up to 64 channels, headphone equalization, and so on. So thank you very much for listening.